All right, you are welcome again. Today, let's talk about partial derivatives, or we simply say partial differentiation. When we talk about differentiation, we are actually talking about a change in a function that depends on a variable, right? But today, I want to talk about a different aspect of this differentiation. Now, let's take a look at an instance. Okay, let's just say the volume of a cylinder. The volume of a cylinder, you can say that it depends on the radius and the height of this cylinder. You get it right? So the radius and the height tells you the amount of the volume. So when we are talking about partial derivatives or partial differentiation, we are talking about what happens when there is a change in radius and the height remains the same. What happens? You discover that there will be a change in volume. We call it partial increment in the volume because there is a partial increment in radius and the height is kept constant. Okay, if we go again and say let's make a small change in the height, you will also discover that it will affect the volume partially. So when there is a change in radius and the height is kept constant, we say that the volume will also change partially. And when there is a change in height and the radius is kept constant, there will be also change in the volume. So these changes is called partial differentiation or partial derivatives. You get it right? Now, let me give you another instance. Let's say we have something like simple interest. We have simple interest to be I equal to PRT all over 100. That is when you want to calculate the simple interest in percentage, okay? But if you don't want to perform this, or if you don't want to find the simple interest in percentage, you can simply say that simple interest is equal to PRT, where you say that P is a principal and then the R is the rate of interest and T is the time. So you discover that this simple interest solely depends on the principal, the rate of interest, and the time. So partial differentiation is talking about when there is a slight change in any of these variables and the rest of the variables are kept constant. For instance, if there is a change in P and R and T remains constant, there will be a slight change in the simple interest. We call it partial derivative with respect to P. That is, there is a change in P. And also, if we go again and say partial derivative with respect to R, that is when there is a slight change in R and P and T are kept at constant. And then we can also go again and say partial derivative with respect to T. That is when there is a slight change in T and then P and R is kept constant. So we say that this is partial derivatives, or we say this is partial differentiations. Okay, good. And then in this lesson, we are going to go higher than looking for partial derivatives. We also go further and see how to find first and second derivatives. Please pay attention to this. It's very, very important. Okay, now let's take, for instance, we have a variable or we have a function f which depends on x, y, and z in the relation of x cubed y squared plus yz squared plus 2z. So in this function, maybe we are asked to find the partial derivative of f with respect to x. What are we going to do? In this function, we are going to differentiate x and hold every other variable constant. That is, we treat x as a normal x, and then every other variable y and z, we take it as a constant. That is, we hold it constant. You get it right? Now let's go. If we say partial derivative of f with respect to x, this is how we write it, okay? Now let's go. in x cubed y squared, if we differentiate x cubed, what are we going to have? We're going to have 3x squared. And then y squared, we hold y squared as a constant. And then if you differentiate y squared as a constant, it remains the same. So when you differentiate this x cubed y squared, taking y squared as a constant, you are going to have 3x squared y squared. You get it right? Good. And then let's go further to yz squared. So in yz squared, there is no x. So all these y and z, we take it as a constant. So when you differentiate a constant, what will it give you? It will give you 0. You get it right? Good. Now let's go to 2z. 2z, there is no x in it. So we differentiate 2z, or we take 2z as a constant. So when you differentiate a constant, it gives you what? 0. So the partial derivative of f with respect to x in this function gives us 3x squared y squared. Let's go again to this same function f and differentiate this function f with respect to y. That is, we are going to take every other function that is not y as a constant and then differentiate y. Okay, now let's go. In x cubed y squared, what do we have there? We have y squared, right? So when we differentiate y squared, what are we going to have? We're going to have 2y. And then we take x cubed as a constant. So we're going to have 2x cubed y. You get it right? Yes, when we differentiate this, we're going to have 2x cubed y. Then we'll say plus. Now going to the second, where we have yz squared. So there is y there, right? Yes, when we differentiate y, what are we going to have? We're going to have 1. And then we treat z squared as a what? As a constant. So 1 times z squared is equal to z squared. And then in the last term, we have 2z. There is no y there. So we take 2z as a constant. And when we differentiate this 2z, it gives us 0. Okay? So the partial derivative of f with respect to y here gives us 2x cubed y plus z squared. Is that clear? Yes. Now let's go again. Still in the same function. Let's find the partial derivative with respect to z. Okay? That means every other variable that is not z, we take it as a constant. Okay? Now let's go. In the first term, we have x cubed y squared. There is no z here. So everything here, we take it as a constant. And when you differentiate a constant, it gives you 0. Now let's go to the second one. We have yz squared. So when we differentiate z squared, it gives us 2z. Okay? It gives us what? 2z. So here we are going to have 2yz. Is that true? Yes. So when we differentiate z squared, it gives us 2yz. Now let's go to the last term. When we differentiate 2z, what will it give us? It will give us 2, because the differentiation of z is what? 1. So 1 times 2, it gives us 2. So the partial derivative of this f with respect to z is giving us 2yz plus 2. You get it right? Yes. Now let's go. Let's take more examples since you have seen the basics. Now let's go further to take advanced. That is, in a situation whereby you are asked to find the first and the second derivative of any function with respect to any variable. Okay? Now let's take a look at this question. This question says, find the first and the second partial derivative for each of the following. Number 1, we have z is equal to 3x squared plus x cubed y plus 4y squared. Then number 2, we have z is equal to 4x squared plus 3xy plus 5y squared. Then number 3, we have z is equal to 3x plus 2y in bracket 4x minus 5y in bracket. Okay, please let's take this one after the other. Okay, now let's go. Number 1, we have z is equal to 3x squared plus s cubed y plus 4y squared. So here we're going to find the first derivative of this z with respect to x. That is, we're going to differentiate this function with respect to x. Every other variable, we take it as a constant and then differentiate x as x. Okay, now let's go. In 3x squared, when we differentiate with respect to x, we're going to have 6x. Is that true? Yes. Plus, now in s cubed y, we take y as a constant, as just in like a number, and then differentiate s cubed. When we differentiate s cubed, it gives us 3s squared y. You get it right? Yes. Plus, the next term, we have 4y squared. There is no x there. So, whatever we have here, we take it as a constant. And the differentiation of a constant gives 0. So, the first derivative of this function y with respect to x gives us 6x plus 3x squared y. You get it right? Good. Now, the question says, find the first and the second derivatives. Now, here we have found the first derivative of this function. We are also going to find the second derivative of this function we have just differentiated with respect to x, and then again, the second derivative of this same function with respect to y. Hello. You know, we have differentiated this function. You get it right? And then we have the partial derivative of z with respect to x. Now, this is the function we are having now. The partial derivative of z with respect to x. So, we go again and differentiate this function we have now partially with respect to x, 1. And then go again and differentiate it partially with respect to y. You get it right? Yes. Now let's go. Let me show you exactly what I'm trying to say. Now we have the function z and we have differentiated partially with respect to x. Now let's go again and differentiate it the second time with respect to x, and then differentiate this time again with respect to y. Now let's go. When we differentiate again with respect to x, we're going to say the partial derivative with respect to x of the function partial derivative of z with respect to x equal to, when you have partial derivative with respect to x multiplied by partial derivative of z with respect to x, is going to give you the second derivative, derivatives of z with respect to x. So when we differentiate this function, 6x is going to give you what? 6. Now we have plus. The second one, we have 3x squared y. When we differentiate this with respect to x, it's going to give us 6x y. Okay? This is going to give us what? 6xy. So this function we have now, 6 plus 6xy, is called the second derivative of the function z with respect to x. Again, we come back to this function. We said partial derivative of z with respect to x, which gives us 6x plus 3x squared y. Now we differentiate this function partially with respect to y. So we call this the second derivative of this function, the z all over the x with respect to y. Now let's differentiate this function with respect to y. So we treat y as y, and every other function that is not y, we treat it as a constant. So in 6x, when we differentiate 6x, it's going to give us 0. And then in 3x squared y, when we differentiate y, it gives us 1. 1 times 3x squared, it gives us 3x squared. All right? Yes. So we say that the second partial derivative of the function z with respect to y, it gives us 3x squared. All right, yes. Now let's go back again to the function z that we have. We say that z is equal to 3x squared plus x cubed y plus 4y squared. All right, yes. Now let's differentiate this function partially with respect to y. So now when we differentiate with respect to y, that means everywhere we see y we differentiate, and then every other variable that is not y we take it as a constant. Okay, now in this function, in the first term we have 3x squared. So when we differentiate 3x squared with respect to y, it's going to give us 0. Now in the second term we have x cubed y. When we differentiate x cubed y with respect to y, it's going to give us x cubed. Then we have plus the last term, we have 4y squared. Differentiating this 4y squared with respect to y is going to give us 8y. All right, yes. So we see that this is the first partial derivative of z with respect to y. Is that clear? Now this partial derivative of z with respect to y that we have, we are going to differentiate this same function with partially with respect to x, and then differentiate it again with respect to y partially. You get it right? Now let's go. We have the function, the partial derivative of z with respect to y. Now differentiating this partial derivative of z with respect to y, differentiating it partially with respect to x, we have it like this. So we differentiate this with respect to x. Okay, so we have x cubed plus 8y. Okay, when we differentiate x cubed, what is going to give us? It's going to give us 3x squared, and then we have plus 8y. When we differentiate 8y with respect to x, is going to give us 0. So the partial derivative with respect to x of the partial derivative of z with respect to y is giving us 3x squared. All right, yes. Now let's go again to this same function that we have. Let's differentiate it again the second time with respect to y. Okay, so we say the partial derivative with respect to y of the function partial derivative of z with respect to y. So we call it the second derivative of z with respect to y. So anywhere we see y, we differentiate. Every other variable we call it, or we take it as a constant. Okay, so in x cubed, when we differentiate with respect to y, it's going to give us 0, because we take x cubed as a constant. Okay, and then we have 8y. Differentiating with respect to y is going to give us 8. Okay, so the second partial derivative of this function with respect to y is equal to 8. Okay, yes. Now take a look at this, please. I want you to pay attention to this. It's very simple. The first thing we did is we have the function, we differentiate this function partially with respect to x. Now this partial differentiation that we have, we differentiate it again partially with respect to x, and then differentiate it again partially with respect to y. So this second differentiation with respect to x and with respect to y, we call it the second derivative. Okay, yes. Now we go back again to the function z that we have, differentiate it with respect to y partially. So we call that one the first derivative with respect to y. Now this function that we have, we call the first derivative with respect to y. We differentiate it again partially with respect to x, and then differentiate it again partially with respect to y. It gives us the second derivatives with respect to x and with respect to y. All right, yes. Now let's take the second example.